Okay, I think it's 3 o'clock. Okay. Hello, everybody, and welcome to the next episode of Inside XRF. I'll be your host today for the next 30 minutes. My name is Konstantin Brendkens. Thanks for joining us. Today's topic will be an example of an application done on the XRF. And the application we'll be talking about are actually multiple applications. And the material group we will be talking about is refractories, or refractory materials, as they are also called. And yeah, we want to give you a quick overview of the material and how we deal with it on a daily basis here in the laboratory at FLUXANA. So let's get right into it and see what is the deal with these refractories. And yeah, let me get started. So presentation. All right, here we go. So we'll start with an overview over the material we are talking about. The German word feuerfest Materialien roughly translates into flame-proof materials, but I think the established term is refractories. So the first question, of course, is what are they? What is meant with this material, or what are refractories, and where are they used? And so we have well, I basically copied this from Wikipedia and filled in a few more details, but we have the definition here. So refractory materials are metallic or ceramic materials which are used for applications on high temperature ranges, so at 300 centigrade to up to 1700 centigrade. And they are in direct contact with this process or the material. So they have a direct contact with the product actually at a high temperature. So they are used, for example, in metal plants or in glassworks, and also in the subsequent thermal processing. So we're talking about casting, shaping, and all the thing where you would heat a metal, for example, to form or mold it into a different form, basically. And so these materials, they need to be resistant to the decomposition by heat, pressure, or chemical attack in order to be efficient and to work with the process. And reality, what we are talking about is powders, or even these bricks. German word here is Schamottsteine, which is basically what is the brick wall inside for example, a converter, or an oven for melting metals. So it's basically a wall that is built from these bricks inside, and it gets replaced every now and so often. In terms of we already touched down on this. So we use them, for example, as furnace linings. So it's the interior of a furnace or a converter. So a big vessel filled with liquid metal, basically. It will have an inlay or a filling made out of these refractory materials, and usually it comes in this form of bricks, and it's basically built up like a brick wall. And yeah, steel industry is obviously a place where this is used a lot, but also cement industry or glassworks. And another thing that comes to mind is these molds for metal casting. So if you want to shape a metal, of course, bending or smithing it basically is one way, but you could also just liquefy it and cast it into a certain form. I think the most common application here is if you think about a church bell or a bell in generally, there would be a big mold that has been built, and it's basically cast with liquid metal to make the form. And all of these materials have one thing in common. And these are the, well, special properties is what we call it. So we are usually talking about a ceramic material. And they have some very exotic elements like yttrium or cerium. And also due to the raw materials where they come from, well, basically how they are produced, we have some impurities, as for example, hafnium is quite common, which is not your everyday analyte you find in your laboratory. And in terms of mechanical properties, they need to be mechanically stable and also very temperature stable, which will be an issue later on down the line. So we have a table here about an overview. There is tons of different materials, and this is only, let's say, a fraction. Well, it's not really a fraction, but there is even more than this list. And we'll be talking about the ones which are outlined in red here. These are the materials that FLUXANA actually has a working application. And we'll talk about those details a bit further down the line. But as you can see, we're basically talking a lot about alumina or silica-based material. Also zirconium and chrome play a role here, and then mixtures of these chemicals. And we'll talk about a bit what does that mean for applications and sample prep later. There is also some carbides in this field of work, which are a bit more problematic. You see, the thing with the carbides is that it's basically poison for platinum ware, so we can't really do fusion with those samples the way we do. So they will not be covered in this. So in this kind of presentation here, we'll be talking about the three groups here. We will have alumina group, zirconium, and chrome magnesite, basically, which are also the active ones we are using in our laboratory. A quick word about the norm, because all of these three methods we are using are norm conform, or normativ, how we call it in Germany. There is a German norm. Yeah, now I need to use either the mouse or the keyboard, then it works. There is the German norm about the analysis of refractories in fluorescence. That's basically the title. And it's quite a nice document, since this one gives you a lot of details and tips and advices on how to do preparation for the different materials in the list, and also gives you an idea about what ranges of calibrations, detection limits, and so on, and CRMs and validation. So it's a pretty big list of all the details. When you want to set up an application for a specific material from the list, you can find a lot of information in the norm, and our methods are based on this norm. So that's the chapter basically about the sample. So we have these refractories. It's quite diverse material, but in general, we're talking about a high temperature and highly mechanical, stable ceramic, let's say. And so the next question for us, if we want to do analysis on this now, we have to think about a suitable preparation method in our laboratory. And one suitable method that was found is the fusion, the dissolving in tetraborate and casting into a glass bead. But there is, of course, a problem here, because due to the qualities of the sample of the material we talked about before, the samples are pretty hard mechanically, and some of these elements are very hard to dissolve. So how do we solve that in preparation? Well, first of all, why do we use fusion? It's mainly because of the accuracy and procedurability, of the high accuracy and reproducibility. By doing the fusion, we eliminate the particle effects. We have no influence of the granulometry anymore. We basically dissolve into tetraborate, and then we have a glass, a perfectly homogeneous sample. Different fusions and parameters can be done for various materials, which is good here because the group is so, yeah, wide basically and different. And also coming back to the norm, it is as the recommended sample preparation in that norm we talked about. So it states for sample prep, fusion is the way to go to get, you know, to get it norm compliant and get the highest security that you can possibly get. What will be our requirements for sample preparation and the sample? In general, sample grinding is important here. As a rule of thumb for fusion preparation, most of our document says we want to go below 100 micron or around about 100 micron. In this case, going below 60 micrometers as a particle size is recommended because this helps with dissolving. And a quick note about the grinding vessel. So in general, when these samples come into the library, they will be coarser. They will be not that fine. So doing a grinding step before the actual fusion is definitely recommended. Also because it helps with the dissolving and yeah, just getting a good fuse speed out of it. And in truth, the tungsten carbide grinding vessel is the only viable option here, simply because it's the hardest inlay you can get for your grinding vessels. And all the other ones, like for example, there is another one which is zirconium oxide. It's also pretty hard in terms of crushing power, but the problem is zirconium is a very important analyte in our material. And grinding always means contamination. We always get something of the vessel inside of our powder and of our sample, and contaminating the refractory with zirconium is not helpful at all. So the zirconium vessel is not a good idea. And the same goes for a stainless steel. We have a chrome steel here, which again will cause problems with contamination. So in reality, tungsten carbide is the best choice here, because it's pretty hard and very effective in crushing down this already hard material or sample. And also the contaminations can be ignored to a certain extent. In terms of fusion equipment, we recommend having a fusion machine with different temperature programs possible, because we will need variation here. Some samples will need longer fusion times or higher temperature to get a good repeatable result. So definitely have a machine which can deal high temperatures and variable fusion timings, let's say. We need a good homogenization, so stirring is important, especially when it comes to the high silica and high zirconium samples. We need a good recipe or a good dilution factor. We have to find an amount of sample that gets dissolved completely and is reproducible in that way. And also, we'll see that later in the results, in the examples. Some of the composition of our specific refractories will place limitations on that dilution factor, so to say. And of course, we need a flux that works and performs well, which in the end, the latest trend is kind of a mixture of tetra and metaborate, which just helps dissolving some of the elements present more reliably. And we need some additives in case chromium oxide is a very good example here. Some of you will probably know that when there is a lot of chromium in your fuse speed, you get this nice green color of the fusion and the bead, but you also get a lot of cracking and breaking because the chrom doesn't like to be dissolved in tetraborate, and it will create tension in the glass. And additives is a way to counter that and still get a nice fuse bead that doesn't break into 100 pieces when it's finished. And yeah, we'll talk about the details in the examples at the end. So we'll talk a bit about how it's actually done. But before we get into these details, we've covered the sample and the preparation. So the final step to making this an application, to actually even making this maybe like a norm conform application, is the measurement method, or the parameters we run on our X-ray spectrometer, and of course calibration. And again, we are referring all of this. It should like we are in this presentation we're talking about conformity to this isonorm, because this is what we do. And so the idea here is to have a calibration method conforming with the norm. So when it comes to the setup of these application, the first question is always what analytes do we measure, or what elements basically, because analytes usually only refers to the things that we give concentration at the end, but maybe we need some extra stuff here. So the first question is, when it comes to the periodic table, what elements do we, like what channels do we introduce into our X-ray? We also need to think about possible contaminations from sample prep, or if you remember, we talked about the grinding vessel made out of tungsten carbide, for example, and that this would be our first step of sample preparation. We should definitely think about possible contaminations coming from that step. So we want to at least monitor the tungsten, and cobalt is also present in those. So these, for example, these contaminations from grinding we want to observe, because they might also be needed for some mathematical corrections, for example. So apart from the actual analytes that we're interested in about the refractory material itself, we also want to have a look at the contaminations from sample labs. And then also we want to have a look at the additives that we might have added in the thing. Like there's this very prominent example of the brome overlap on alumina. So obviously, if you're using lithium bromide as an additive, we would want to measure the bromine overlap as a correction on alumina, because this might actually, well, in the alumina-rich materials, this is one of the main interests. And I pressed again. I should stop that. Okay. And also, we when it comes to the measurement parameters, we want to make sure that we maximize intensities in order to meet the validation requirements which are required. So what does that mean in practice is that we usually want to find the maximum in intensity, but also in preparation we want to find the maximum amount of sample, because that gives us higher accuracy in the end, and it will be kind of required in order to actually meet the requirement of these packages. So there are some packages or calibration standard sets available. You know, the FLUXANA sets you're probably familiar with. What do they consist of? They are a mixture of usually synthetic standards and CRMs. There is a certain amount of CRMs available, but we found that a lot of the ones that we need, like to cover the ranges, we need synthetic ones. So those are mixtures of primary oxides, basically. The ranges are specified in the groups or in the norm. We will talk about the details here a bit later. And it is possible to combine some of these different refractory groups into one application, because chemically they are very simple. And that's why we'll see, we'll have the table next again, and we'll see that there is a certain overlap. So you can have one analytical method in preparation that will allow you to analyze multiple of these refractory materials, which is of course a boon. To have like only one method for multiple materials always helps, like with time and everything. The validation of these sets always works on CRMs, on certified reference materials. And there is usually the validation works on these tolerance factors, which are basically, they are depending on concentration of the oxide, which basically means each element has an FT that you can just look up in the list. And the higher the concentration range you're operating is, the higher the FT. And then the target should always be that the reproducibility inside, or the reproducibility, sorry, should always be equal to the tolerance factor, and the accuracy, so the analysis between two labs should always be equal or less than 2 times the tolerance factor. So we already spent enough time about the theory, so let's have a look a bit at the details. So we'll be looking a bit into our examples here, and as you can see, I mentioned before, we can combine similar materials. So example 1 is the first one here. It's alumina-rich materials and aluminosilicates, and we'll start with, yeah, this is a nice name, so that's the actual name of our application, but I think more interesting is what ranges are we covering. And I'll leave this on the screen so you can pause well, you can't pause right now, but later when you watch the video, you can pause it here. So you have the elements here. Remember, we talked about some of the exotic ones, hafnium, yttrium, and also about the impurities, tungsten, and there is some molybdenum here, I think. No, in this case, it's not. Well, we have the ranges here, and it's basically limit of quantitation or minimum value up to maximum. And so this is the definition of your application if in this example. And preparation details are now, we are taking the powder as it should be, like the particle size should be smaller than 100. So in this case, grinding in a tungsten is recommended. We then do our fusion mixture would be, we take 1 gram of the ignited sample. Ignited means we had it in a muffle furnace at 1025 centigrade until mass constant, which usually translates into, let's say, roughly 1 hour. I would even go as far as to say that half an hour should be enough, because refractories are already burnt material. Like, there is not much in the ways of LOI here, unless there is like a carbide as part of the refractory, which again is not covered here because then it gets really complicated. But in this example, we just do the ignition until mass constant. 1 gram of that ignited powder we take, we mix it with 8 grams of flux. The flux we use here is our trusted X65, which is 66% tetraborate, 34% metaborate, good for dissolving a lot of different chemical components. We use an additive here, which is ammonium iodide solution, and it says here if needed. So we usually try without, and if that fails, we add a few drops of that solution. And you can see it here, it comes in these little bottles and you just put it on top. And then the fusion program would be A1 on our Vitriox electric, which roundabout is like, let's say 20 minutes at 1250 degrees centigrade. Around about 5 minutes of fusion to get it liquid, and then the rest is just agitating and homogenization. And we can adjust those. Some of the standards we found that they need even longer than that. Again, I mentioned before, silica and zirconium can be problematic. And if we take 1 step back, you can see here, for example, the silica range is up to 100 in this application. So high silica sometimes even needs more time. I need to sort of rearrange here because I can't really see what I'm talking about now. Okay, so sample prep, we had the details. So how about measurement method now? First of all, what do we measure? What elements, analytes do we have? Well, basically all of them. And where do they, well, all of from the list. We have all the element materials, and that includes these sort of exotic ones. Even they might not be important, but they are present. So we still calibrate them in the method as well. We have our possible contaminations due to sample preparation. So in this case, for example, grinding, we have the tungsten here. And last but not least, we have possible overlaps. And this on the right is an actually printout of the method. And as you can see, there's quite a lot of line overlap corrections here. For example, cobalt gets corrected with eisen and hafnium. One reason why we have to have the hafnium as an analyte line. The more interesting overlap here is there is a major overlap of iodide on titanium. So titanium is interesting here as an analyte, it's important. And the iodide comes from preparation due to the additive. And the overlap is, as you can see here, this is a spectra. We have a scan of 2 samples here. Both of them don't contain any titanium. They are both blanks chemically. But as you can see, the blue one here is prepared with the iodide additive and the red one is without. And you can see the lines are right smack on top of each other. So important to have an overlap to get a good concentration analysis here. And notice that the overlap is actually the L beta, but we make an overlap with the L alpha. That's just the trick because the ratio between L alpha and L beta is always constant, so you can do that. And the L alpha is just easier to measure. But we need to introduce an iodide line as an additive line here to make that overlap. Second example, we have the zirconia-rich materials. So we have refractories rich in zirconia. Again, we have quite a different range here. Notice the aluminum doesn't go up. We have some other analytes. Silica isn't that high, but of course, zirconia is quite a lot. So that's kind of the special here. And zirconia is also silica and zirconia both have kind of similar characteristics when it comes to fusion. So let's have a look at the details here. Materials rich in zirconia oxide. Again, grinding and pretreatment would be the same. We grind it down to a fine powder, which helps in dissolving it then. The ratio sample to flux is different. In this case, we only use 0.5 gram of ignited sample. Treatment is the same here. We do treat in the furnace until mass costs at 1025, and then the flux is 8.5. So the total is the same, but the ratio is almost double. Also, flux is the same, and again the additive is the same if needed. So we add it when necessary. And also fusion parameters is the same. Now, why do we only use half the sample amount here? You remember earlier I mentioned that we have an accuracy target, and the more sample we use, the easier it is to meet that accuracy target. The reason is the zirconia here. Like it is really difficult to get this into a homogeneous bead because even if you play with longer temperature programs, it's difficult to dissolve. It's even more difficult than silica. So that's why we need to use a higher dilution factor. We need to use less sample in order to be 100% in dissolving here to get a good bead. We want to kind of highlight a different thing here in this application. So we'll talk a bit about the calibration sets. This calibration set in particularly, refractories, zirconium oxide is made up of 16 synthetical standards. So you can see them here. They're all basically done from primary oxide. And additionally, we have 3 CRMs here just to kind of match the synthetical ones. And then for validation, again, we use a mixture. We take 2 CRMs, powder CRMs as validation sample. And then the last one is a synthetical validation sample, which comes as a so-called glass powder. That basically means we made this sample from primary oxides, and then we fused it and we ground it down again so that you get basically a powder which is already homogeneous. And yeah, in the end, zirconium is the interesting analyte here. And just to highlight how it performs, we have the actual curve from our spectrometer here. And the orange samples are the 3 validation samples we just talked about. We have the 2 CRMs and the synthetical one. And yeah, the standard estimated error, the Reststreuung is 0.3, which is, I think, very respectable if we're looking at the concentration range from from 60 to 100% here. Final example, and we need to actually hurry a bit because I'm already doing overtime. Chrome magnesite, or chromium alumina. So again, it's a combination of different materials. We have the matrix here, again, a lot of silica, but of course also a lot of chrome oxide. And that will be kind of the determining factor here. Let's have a look at the preparation details. In this case, we actually grind longer because, again, chromium, a problem with dissolving, so we need as fine as powdered as we can get. So grinding and taking the lower parts of the is a good idea. We take the high dilution factor, 0.5 and 8.5. Again, because if we use more, it will never work. The beads will simply break once they solidify and cool down. And as additive, we use lithium bromide here all the time. Every bead we make gets its share of lithium bromide. Again, the reason here being the chrome oxide, it just simply doesn't work without. Fusion parameters, this one, in our lab at least, we did that one with the gas machine. The other ones were on the electrical. This one is on the gas, though you could just switch them around. It's not impossible. It's just that we had that from a historical point of view. Like we did it that way, and we just kept using it. So we use program one here, which pretty much mirrors the same parameters. It's round about the same temperature, although it's an open flame machine, so not that, how to say, precise. And there is a very special thing here that we'll talk about here, is that we can even use a higher dilution for the samples that have more than 30%. Now, what does that mean? That means usually for samples which are below 30% in chrome oxide, this is our recipe. But it is possible to, in case you had, like, let's say we have 35%, then we only use, and I used the mouse wheel again, I'm sorry. Technical difficulties. Yeah, this is, when we look at the standards, let's maybe do it that way. The standard set here consists of 13 CRMs, all of them done with 0.5 grams of material. That's what we mean with 100% weight. Then we have another 11 synthetical ones, which also follow that rule. The sum of analytes here will always be 100%. We only have a few examples here, but you can see the sum of analytes is 100%. And now we have our additional CRMs, which have 50% weight. And that's what is meant with we can use a higher dilution factor. In this case, we don't use 0.5 gram of sample, but we use 0.25. So we only take half of the amount, thereby lowering the chemical concentration in the bead and preventing breaking and preparation to make it possible, because everything above 30% just breaks half of the time or even more often. And then for validation, we use CRMs and synthetical validation here again. And the trick basically is that when calibrating this in the curve, by doing this, we call it double dilution here, which is not completely correct, but since you're using only half the sample, it kind of describes the purpose. Calibration-wise, this is our curve. And you see here the blue points in the middle are the ones which have 50%. So these are the ones that are not 0.5 gram, but 0.25 gram of sample material. And all the other ones are 0.5. And you can see by the bending, this is done then also quadratically, but I think it's the details. The thing is, by using this double dilution, we kind of trick the software and we come back to a linear area of our calibration curve. So in the end, to prevent problems in preparation, we do this trick and we solve it mathematically then. And yeah, as the summary, just to round up, we talked about our samples. So when you want to do a refractory analysis, the first question is, what is your material group? Or is it even a group, or is it different materials? What other refractories you want to analyze? And then you can group certain ones which are similar. Some are not. Sometimes you have to split them to get the high accuracy that you want to achieve. The preparation details, again, you've seen the list of the different refractory materials, and there is lots of details here. So it really comes out to trying. And yeah, feel free to ask us about some advice, because we've been doing most of those mistakes and solved them. So we can definitely give you a tip or two. Standards and measurement method is what CRMs are available. Do we need to go synthetic or do we need to trick? And then analysis wise, we have to choose which are the analytes of interest for our analysis, but we also need to think about the contaminations from sample prep on additives, and to make sure that we get all the information that we can calibrate later. And yeah, the final results should be a results evaluation or an analysis that gives you reliable and repeatable measurements, maybe even norm according. That's up to you, but definitely the best result possible for your material and your refractory. And yeah, that's it. Thank you very much for your attention. Sorry for keeping the extra 5 minutes. It actually was more than I was expecting. Thanks for the attention, and I'll see you next time, hopefully. Have a good one. Bye-bye.